One thing that gives students a lot of trouble is knowing how to read and use a two-way table or a contingency table for probability questions. Here's a table that summarizes hypothetical results for a cancer screening of 1,000 random individuals. I left the total columns blank so that we can fill those in ourselves. What happened was 1,000 people were screened for cancer, and then it was later determined whether or not those individuals actually had cancer or whether or not the screening was incorrect. From this study, there were 8 people who had a positive cancer screening result and actually had cancer. 2 people had a negative cancer screening result but actually had cancer, which means that the screening failed to catch the cancer that was really there. So in total, the number of people in this study that had cancer was 10. 8 people who had a positive test and cancer, and 2 people that had a negative test and cancer. In this situation, we could easily add the 8 and the 2 and see that that was 10, but we can also have Excel do the work for us just in case it gets more difficult later. So in the total column next to cancer present, I'm going to type equals sum and then open a parenthesis and highlight the 2 cells, cells B4 and C4, that have the cancer present in them. Pressing enter, we see 10 appear there. Next, I need to add up how many people in total had no cancer present or cancer not present. So that would be the 99 people that had no cancer but had a positive test result, and the 891 people who had a negative test result and actually did not have cancer. So we could add those. Since I used relative cell references to find the previous sum, I can fill down into cell D5, and it will automatically add cells B5 and C5 for 990 people did not have cancer. Next, we can add up how many people had positive test results in total. So we have 8 people had cancer and a positive test result. 99 did not have cancer and had a positive test result. So I'm going to add those two, equals sum. I'm going to highlight cells B4 and B5. Pressing enter, we see 107. And finally, similarly, we're going to add up the number of people who had negative test results in total. Since I used relative cell references, I can just fill to the right and it will update and add cells C4 and C5. 893 people had a negative test result. And finally, the total number of people in the study altogether, I can fill to the right one more time, adding 10 and 990 for 1,000 people, just to double check to make sure that we have everything right. Anytime you're given a two-way table, or maybe it's sometimes called a contingency table, we want to add in those sums for the different categories, so the sums of the rows and the sums of the columns. It will help us answer questions that are called conditional probabilities later on. So we have a few questions we're going to consider using this table. The first one says, find the probability a randomly selected individual in the study has cancer. The easiest way for me to answer questions about probability is to find what the denominator, the bottom of the fraction, should be first. This problem is asking for the probability that somebody that we pick in the study has cancer. We know that a total of 10 people have cancer, and the fact that it says we're picking randomly from the whole study means that we could pick any of the 1,000 people in the study in our selection. The probability that a randomly selected person from the study has cancer, the denominator will be 1,000 since we're picking from everybody, and the numerator is 10 since that's the number of ways I can pick somebody who actually has cancer. So to do that in Excel, I'll type equals 10 divided by 1,000. We see that's 0.01 or 1% if we want to express it as a percent. The second question says, find the probability a randomly selected individual in the study had a positive test. So very similar to the previous problem, we're picking randomly from everyone in the study, so the denominator is 1,000. The probability that somebody has a positive test will be the number of positive tests we have, 107 positive tests, 8 from people who actually had cancer, and 99 from people who ended up not having cancer. 107 out of 1,000. We type equals 107 divided by 1,000 in cell A11, we see 0.107, or about 10.7%. Number 3. Given that a person in this study has a positive test, what is the probability they have cancer? This problem has a key word in it that should jump out at you. It says given. Given means that we're looking for a conditional probability. We're given certain information that restricts who we're looking at, who we're selecting from. The word given will restrict our denominator. No longer are we picking out of everyone in the whole study. We're only picking from among the ones who have the condition after the word given. So here we have given what? Given that the person has a positive test. So we're only picking from the ones in the study who had a positive test. In this situation, from the table, we see the total under positive test is 107. 107 people had a positive test, and that's all we're picking from. So the denominator is 107. We're looking for the probability that that person has cancer. So how many of those 107 positive tests actually had cancer? Well, only looking in this column under positive tests, we see 8 people had cancer, 99 did not, for a total of 107. So the probability we're looking for is 8 out of 107. About 0.07, about 7, maybe close to 7.5%. So let's pause for just a second and consider what this means. We know that the person has a positive test, which means they took some cancer screening, and the cancer screening came back positive, meaning that the cancer was detected, or they had some reason to believe that this person had cancer. Now, once someone receives that terrible news, they say something like a preliminary result indicates that there may be cancer present. Then there's follow-up studies done to verify whether or not there really is cancer there. They might start with something like a blood test or something like that, and then move on to something more invasive in order to verify. So in this situation, we know that the first screening, there were 107 people who received a positive test back, but only 8 of those, only about 7% of those, actually ended up having cancer. And that's why you often hear that hearing the news, you may have cancer, initially is very scary, but oftentimes will be followed up with a comforting statement. Don't worry, there's still less than a 10% chance that you really do have cancer. What they are referring to is this phenomenon we see here, where the initial screening will capture a large portion, relatively speaking, of people who may have cancer, and then later we determine whether or not they actually have cancer, and it's less than 10%. In this case, it's about 7.5%. The fourth question. Find the probability that a person in this study has no cancer given they have a negative test. So again, the keyword given needs to stand out. We're going to restrict our denominator to only the condition that's given after the word given. So given what? Given they have a negative test. We're only looking in the column negative test. The denominator is 893. We're only picking from the 893 people who received a negative test. So what are we looking for from those 893 people? We're looking for has no cancer. The probability they have no cancer given that they have a negative test. So equals, the numerator is how many of those people who had a negative test did not have cancer, 891. So I'm going to type equals 891 divided by 893, 0.9977. So this is more than 99%. The probability that a person has no cancer given that they have a negative test is very high. It's very unlikely that someone who gets a negative test will actually end up having cancer. Question 5 says, are the events cancer present and positive test dependent or independent? So we need to remember what the definition of independence is, and I want us to use the mathematical probability-based definition. The probability-based definition says that two events are independent if the probability of seeing one event occur does not change if we see the other event occur first. Another way to put that is the probability of the first event, A, is the same as this probability of that same event, A, given that we know the second event, B, has occurred. So we look at the event A and say, what's the probability of A happening? And then we compare that to say, okay, if I know B already happened, given B, if I know that the condition B has already happened, does that change the probability of A? If those two probabilities are the same, meaning the probability of A did not change with the new information that B has already occurred, then we call those two events, A and B, independent. The probability of A happening did not change with the new information that B happened. So the opposite of that would be dependent. If the probability of A does change, if we know that B has already occurred, then A and B are dependent. Watching B happen changes the probability that A happens. So we can call event A cancer present and event B positive test. First, we need to find the probability of cancer present on its own, probability that cancer is present. And we can do that by dividing out of the 1,000 people who were in this study, how many of them had cancer present. So we answered this question already. It was the answer to number 1. The probability a randomly selected individual has cancer. That's 10 out of 1,000. So 0.01. We're going to compare that to the probability that A happened, or the fact that the probability that cancer is present, given the second event, given we have a positive test. So I'm going to put that in notation first. Probability cancer present given the vertical bar positive test. Meaning I'm going to restrict my denominator to only those that have a positive test. According to the table, we had 107 positive tests. Out of those, how many had cancer? There were 8 of them. This was the answer to number 3. Given that a person has a positive test, what's the probability they have cancer? Just to calculate it again, it was equals 8 out of 107. That 0.074766 and so on, about 7.5%. So if these two probabilities are the same, then the two events are independent. Since they're not the same, these two numbers are different. 0.01 is different than 0.07. These two events are dependent, and that's what we're going to say. Since the probability of cancer being present changes with the information that the test was positive, these events are dependent. Anytime you're asked to find out whether or not two events are independent, you need to calculate two probabilities. One of them is the probability of an event on its own, like we found the probability of cancer, and the other one being the conditional probability of that same event, probability of cancer given the second event, given positive test. So the next question, I think we have 2 more. If 2 people are chosen from this study at random without replacement, what is the probability both had a positive test? 2 people chosen from the study at random, which means we're not giving any conditions to this. We don't see the word given anywhere. We're picking from all 1,000 people in the study. We're picking 2 people without replacement, which means we pull one person out, hold them out, and then we reach in and pull one other additional one out. What is the probability both had a positive test? I like to phrase it using the notation probability of, we're looking for positive test, probability of positive test, and then positive test. Another way to phrase it would be the probability the first person is positive and the second person is positive. This involves the multiplication rule. Anytime we're being asked to find two events with the word "and," like both have a positive test, first person and then second person, or anytime we use the phrase "and then," like two events happening in sequence, one and then the other, we're going to end up multiplying the probabilities. And since that we're reaching in without replacement, the probability the second person has a positive test changes because we are pulling one person out, and we need to recalculate the second probability based on removing that first one from the pile we're pulling from. So the first event, the first person having a positive test, the probability the first person is positive, is we're reaching in and pulling out of all 1,000 people. How many of them had a positive test? 107 did. So the first one is equals 107 divided by 1,000. The next thing we need to calculate is the probability that the second one has a positive test, given that the first one that we already pulled out has a positive test. It's a conditional probability. Probability second positive, given the first was positive. Because in order for this compound event to occur, the both have a positive test, we need the first one to be positive, and then also we need the second one to be positive. The probability the first one is positive is 0.107. Probability the second one is positive, given that we already have one of the positive result patients or people in the study taken out. Well, how many do we have left? We have a total of 999, and from those we took out one of the positive tests. We have 106 left. So equals 106 people that are left in the pool that we're picking from have a positive test because we took one out, divided by 999 people total left. We see 0.106, so the probability did not go down that much. And according to the multiplication rule, we multiplied these two probabilities. So the probability of the first one being positive times the conditional probability of the second one being positive, given the first one was. So probability of both positive is the first one times the second one. So 0.107 times 0.106. I'm going to use cell references to avoid rounding error. 0.01135, a little bit more than 1%. Okay. Finally, the last question. What is the probability that a randomly selected person from the study either had a negative test or no cancer? So the key word in this question is the word "or." We're looking at one randomly selected person from the whole study, so the denominator is 1,000, and we're looking for either one or both of these events, negative test or no cancer. So we'd be satisfied if the person has a negative test and cancer. We'll be satisfied if the person has a negative test and no cancer, and we'll also be satisfied if the person has a positive test and no cancer, because any of those situations being applicable will make us satisfied. We've satisfied the event. So probability negative test or no cancer. This is the addition rule. The addition rule says that the probability of either one of two events happening is the sum of those two events, except we want to subtract out whether or not there's any overlap in those two events. So with the negative test, if we look at the table, we have 893 people had a negative test out of 1,000. So 893 out of 1,000. 893 divided by 1,000 is 0.893. And we want to add to this, we want to add no cancer, the probability the person has no cancer. So in the study, 990 people in total had no cancer. So equals 990 divided by 1,000. The issue with this is if we were to add these two probabilities as they are, we get a number larger than 1. These two numbers added together is something like 1.8, 1.9. So we know that it's not just these two added together because we would get something that's not a valid probability from doing that. So there's something else going on. We need to subtract the overlap between those two. In our table, the cancer not present overlaps with the negative test. What we're doing is we're counting these 891 people who had a negative test and had no cancer. We're counting them twice. We should only count them one time. So really, ultimately, we only want these 99 people who had a positive test and no cancer, these 891 that had a negative test and no cancer, and these 2 people that had a negative test and had cancer. Those are the only people. There's only 3 categories that will satisfy the condition that we have. So we're going to subtract the way the the way the addition rule says it is we add the 2 probabilities and then we subtract the overlap. In this case, the overlap is 891 out of 1,000 equals 891 divided by 1,000. And I see that we're subtracting 0.891. So I'm going to do that all together now. I'm going to use my cell references. I have the first probability in cell C25. I'm going to add the next probability in cell, for me it's in cell E25, and subtract the overlap, which was in cell G25. We see 0.992. The probability that a randomly selected person in the study has either a negative test or no cancer, 0.992. So a quick recap. What did we do in this exercise today? We learned how to use a two-way table to find these total columns and rows that will be useful for us. We learned how to use the two-way table to find a probability that an event happens. We learned how to find a conditional probability where the keyword is given. We also learned how to determine whether or not 2 events are independent based on the numbers in the table. And then we talked about how to use the multiplication rule in a situation where we're not replacing when we're pulling out multiple individuals. And the last question was using the addition rule, finding the probability of 2 events, either one of 2 events happening using the keyword or, and subtracting the overlap.